Okay, here we are in chapter 12, finding square roots.
All right.
This chapter, some of you have probably seen square roots or radicals, another term for these, in your past. Since the definition is what number squared equals 81, when we look at this, what number would be squared that equals 81?
Or another way to think of that is what number do you multiply by itself to get 81?
In this situation, that number is 9. By definition, 9 squared equals 81. Therefore, the square root of 81 equals 9. If you remember that principle throughout this chapter, you'll do fine. So let's look at the second one. We have the square root of 9. So again, you ask yourself, what number squared or what number times itself equals 9? In this situation, that number is 3. So therefore, the square root of 9 equals 3. Let's look at some more. Here we have some negatives involved. Every now and then this throws students a little curveball when they're doing these. Just remember your order of operations. We're going to take care of what's underneath the radical first, and then we'll deal with the negative. So for this first problem, we're asking ourselves, what number squared is 49? Well, that number is 7. So if we want to do this, we can strike out the square root of 49 and put a 7, and now we're just going to carry the negative sign down. So our answer is negative 7. In our second example here, we have the square root of negative 4. Now remember, if you recall the definition, we're trying to figure out what number squared equals negative 4. Bill?
Yeah, chances are there are no numbers that you can square to get negative 4, because if you square any number, the answer is either positive or 0. So for a problem like this, actually there's no real solution. So this problem pretty much can't be done.
That's it. We're going to leave this one alone. It is done or not possible. Some books might actually put NP next to it for not possible. Okay, let's move on. Now with variables, some students find variables more difficult initially, but I think by the end of this course or this chapter, you're going to find that these are the easiest to deal with. We'll start with the first one, going the long way. Since we've already studied exponents and exponent laws, we are trying to find out what number squared equals x to the 8th power. Now this is a little tricky to look at, but in other words, what variable squared would become x to the 8th? And when you think about your rules of powers, the power to power rule, you're asking yourself, power times a power is how we come up with 8. So if you substitute it, or if you think of x to the 4th squared equals x to the 8th, then you came up with the right answer. The square root of x to the 8th is x to the 4th.
Again, another way to think about this, if you multiply x to the 4th by itself, x to the 4th times x to the 4th, when you multiply the x's, you add the exponents. Sure enough, 4 plus 4 does give you x to the 8th power.
Yes. Now, we do have a shortcut, and we would be remiss not to share this with you. When we see radicals, we never imagine a 2 in here, but when you get to cube roots, fourth roots, and other roots in intermediate algebra, they'll start placing some alternative numbers here. Let's just say there is a 2, and there is, for the sake of discussion here. This 2 divides into 8 4 times. There's no remainder, therefore we have no radical remaining. So if you like that rule, you can use it. Matter of fact, you might find it to be much easier when we get to the more complex radicals.
That's right. So basically, Jerry is just saying this. If you have the square root of x raised to a power, just divide the exponent by 2, and that'll give you your answer. So the square root of x to the 8th, 8 divided by 2 is 4, so the answer is x to the 4th. This works as long as you have x raised to an even power. We'll talk in a little while about what you do if you have an odd power.
Okay, so let's apply this rule to the second one. Again, imagine a 2 here. 2 divides into 4 twice, no remainder, and then 2 divides into 6 3 times with no remainder. That is the final answer.
And remember, it's easy to check your answer. To make sure this is correct, just multiply x squared y cubed by x squared y cubed. The x squared times x squared is x to the 4th. The y cubed times y cubed is y to the 6th. Sure enough, when you multiply it by itself, you end up with the expression you started with, so your answer has to be correct.
There we go. Moving on. Our next problem. Now we end up with some that aren't as pretty as our other ones. It's exactly what Bill was alluding to earlier. Again, let's imagine our 2 on both of these problems. We'll start with the first one. 2 goes into 9 4 times. However, there is a remainder.
That's right, there's a y left over.
And that remainder, the 1, is what you leave under the radical. Now, we don't normally leave the 1 on there, but for the sake of discussion here, let's just do it, okay? But that is your final answer, y to the 4th times the square root of y. In this second problem, again, we have 2 odd powers, so we're going to have 2 remainders. 2 goes into x cubed 1 time with a remainder of 1. And then 2 goes into 5 twice with a remainder of 1. So this, take out the 1s, is your final answer.
Now, Jerry, I usually teach these a slightly different way, so let me do this second problem the way I would show it, in case anyone finds this any easier. I usually tell my students that I know how to do these problems if the exponent is even. I just have trouble with them if the exponent is odd. So what I do is I rewrite the problem in terms of the even number that's closest to the number they gave you. So, for example here, I'll think of x cubed as x to the 2nd power times x to the 1st power, because 1 less than 3 is 2. And I'll think of y to the 5th as y to the 4th power times y to the 1st power, again, because 4 is 1 less than 5. And now I can use the rule from the previous screen. I know the square root of x squared, it's x to the 1st power. I know the square root of y to the 4th, it's y to the 2nd power. But I don't know the square root of x to the 1st or the square root of y to the 1st, so those just stay over here under the radical. This will also give you xy squared times the square root of xy. Again, there's really not that much difference between the way Jerry does it and the way I do it, but we want to make sure we show you alternate ways so that if one of them seems easier to you, you can stick with it.
I like that idea, Bill.
All right.
Okay, this next part, we're going to find square roots of fractions. Now, when you see a radical that has a fraction underneath, the first thing you want to do is see if you can simplify it underneath. Is there a common factor that will reduce the fraction? If there's not, then it's probably easier to go ahead and just break this up into 2 parts. The square root of 1 over the square root of 25. In other words, look at the numerator and denominator separately. Once you do that, you'll see, this is one of those perfect squares. Square root of 1 is equal to 1. Why? Because 1 times 1 is 1. Square root of 25 is 5, again, because 5 times 5 is 25. Once you finish that, this is your final answer, 1/5. In the second problem, we just added a negative sign in front, but we'll still approach it the same way. Since there's nothing common that can reduce 9 over 64, we'll break this up into the square root of 9 over square root of 64. This gives us the final answer of negative 3/8. Again, 3 times 3 is 9, 8 times 8 is 64, the negative just carries over. If the negative was under the radical, it wouldn't be possible, but because it's outside the radical, it just carries to your final answer.
That's right. The only thing I want to add is don't forget to keep carrying that negative on the outside along. What sometimes happens is students notice it in the first step, but then forget about it later on. So make sure you keep copying that negative down.
Okay, this next problem involves our square roots of variables. And again, we're going to approach this the same way. Step 1, let's separate the fraction into the square root of a to the 7th over the square root of b to the 6th. Now, in the numerator, the 7 is not a perfect square. So again, if you remember the rule, the imaginary 2 that exists out here, divide 2 into 7, and it goes in there 3 times, with a remainder of 1, or just a. In the denominator, 2 divides 6 evenly 3 times, with no remainder. So our final answer, a cubed times the square root of a over b cubed.
All right. Let's keep going. Now, before we go any further, if you have a calculator, even though you're not allowed to use one in this class, your calculator will give you a decimal value for the square root of 20. But when the problem asks you to simplify the radical, it's not asking you to give that decimal answer. That's not the question that's being asked. The question that's being asked is rewrite this so that the expression under the radical can't be simplified any further. So it's important to understand that, because occasionally I have students who will bring a calculator in and say, my calculator says the square root of 20 equals this. Why isn't that the same answer that we're getting? The answer to that question is that's not the question that you're answering in these problems. What you're trying to do in these problems is simply put the radicals in a simplified form in the same way that we simplify fractions by reducing them to lower terms.
Couldn't have said it better myself. When we look at these, we're going to take a little different approach than we have with the other ones. The first thing I'll recommend that you do, if radicals are not common to you in perfect squares, is actually write out all the perfect squares starting with 4. I'm going to put them actually at the bottom of the screen here. We've got 4, 9, 16, 25, 36, 49, 64, 81, and 100. And for the sake of this course, that's probably about the limit of what you need to know.
Right, yeah, you're not going to see any number larger than 100, I don't think, in these problems, yeah.
Now, we don't want you memorizing these. These are, you can easily think about these and write them down. Think of 2 times 2 is 4, 3 times 3, 4 times 4, 5 times 5, and just write that list down. As a matter of fact, you might want to write it down as soon as you get to your first radical problem. Because here's what we want to do with it. When you see a number like square root of 20 and you realize it's not a perfect square, in other words, a number times a number does not give you 20, or the same number times itself does not give you 20.
There is no number you can multiply by itself that gives you exactly 20, because 4 times 4 is 16 and 5 times 5 is 25. 4 gives you 16, that's too small. 5 gives you 25, that's too big. So 20 is not a perfect square.
It is not. So what we're going to do, we're going to scan our list down here and try to find the biggest perfect square, that's what we'll call these, the biggest perfect square that divides 20 evenly. Well, you'll notice that 20 falls right here between 16 and 25, just as Bill said. So going left, we say, does 16 divide 20 evenly? No. Does 9? No. But 4 does. So what we're going to do, we're going to branch this off, and we're going to start with our perfect square. Write it first. 4 goes into 20 5 times. So break it up into the square root of 4 times the square root of 5. Then, since we already know what the square root of 4 is, strike through that and put a 2, and then carry down your remaining radical. This is the square root of 20 simplified.
That's right. And again, it's simplified because now there is no perfect square in that list that will divide evenly into 5. That's what we mean by a simplified radical.
Yes, and if you were allowed to use a calculator, if you found the decimal form of radical 20 and then found the decimal form of 2 radical 5, you would find that they're the exact same number.
That's right. So one way to check these answers, if you do have a calculator around, is to compare the decimals. If the 2 decimals match, then pretty much you're guaranteed your answer is correct.
Yeah, you at least haven't done anything wrong. You may not have gotten the lowest terms, but you definitely haven't done anything wrong in what you've attempted. Now, the second problem over here, same principle. We have a 3 in front, but we're just going to carry that down. And then we're going to look at radical 32. It falls right in here. And then going left, we say, well, 25 doesn't divide 32 evenly. 16 does. So we want to break down 32 into 16 times 2. Okay? Now, the 16 is the perfect square, so we wrote it first. We know that the perfect square, or that the square root of 16 is 4. We have the 3 and the 4 together now, and since they're both not under a radical, we will actually multiply those, and we end up with a 12 radical 2 as our final answer.
All right.
Now we're going to combine both operations, our operations with variables and our operations with numbers. One of the suggestions I give my students in the classroom is to first break these up. Break it up into the square root of 27 times the square root of x to the 6th. The reason why we do this is because there's two different rules that we're kind of using to simplify these. This one we're looking for a perfect square and we're taking it out. Here we've already discussed the shortcut rule, which is just to divide 2 into 6. So we start with a 27. If you still have that list written down, you will see that the square root of 9 is the only perfect square that divides 27. As far as this term over here, you divide 2 into 6, and you simply get x to the 3rd. There's no remainder, so no radical remaining. Now, the square root of 9 is 3. So now we have a 3, a radical 3, and an x cubed. Well, the final answer, we're going to take everything that's not under a radical and write it together. Number first, variable second. If there's more than one variable, put them in alphabetical order. Same thing goes under the radical. Number first, and if there were any variables, they would come second in alphabetical order.
That's right. In doing these problems, you always put the radical last, and mainly this is just done traditionally because it's a little easier to read. Jerry's answer there, 3, the square root of 3 times x cubed, is not actually wrong, but most people would prefer it to be written as 3x cubed, the square root of 3. The reason for that is if you put the x cubed after the square root of 3, it's not always obvious whether the x cubed is under the radical or just next to the radical. This way, if you put the radical last, it's easy to see what is under the radical and what isn't under the radical.
Yes, teachers don't like multiple choice tests.
That's right, yeah, and
students.
remember, we're the ones who are grading it, so you should probably put them in the form that we like because we'll be grading it.
Absolutely. Okay, our next problem, same principles here. We're first going to separate these into two radicals, the square root of 98 and then the square root of x, y to the 7th. Now, a little bit more challenging on both ends of this. As far as the 98 goes, if you look real close, you will find that the square root of 98 is divisible by 49. And 49 times 2 is 98. Again, if you have that list written on your paper, this will not be rocket science. But if you're just trying to come up with this on your own when you're looking at a problem and you have test pressure, amazing how you forget a lot of stuff.
That's right. So we do recommend that you keep that list in front of you in doing these problems. It's amazing how much less stressful it is.
It sure is. Now, over here, we're going to apply our division rule by 2, and this is one of our first situations where 2 doesn't divide a power. Well, if it doesn't divide it, it just means that's going to stay under the radical. So we go to the y value. It has a power of 7, so 2 goes into 7 3 times with a remainder of 1. And then our x, we couldn't do anything with x, so we just leave that under the radical. Now, simplifying our square root of 49 over here, that gives us 7. And now we see we have a 7 and a y cubed, both outside the radical. Under the radical, we have a 2, an x, and a y. Using the rules that I gave you before, put these number first, variable second, and then under the radical, number first, variable second, and alphabetical order. The problems don't get any harder than this.
That's right. Jerry just said what I was about to say. This is about as hard as one of the problems will be, at least in this class. If you can do this one, then you pretty much have these, you pretty much understand these as well as you need to.
Yes.
All right.
Okay, these next problems, adding and subtracting radicals, when you first look at this, you might go, oh my, this is totally different than what I've seen. In actuality, this problem is nothing different than a problem like this. 3x minus 4x plus x. Now look close and you'll see the relationship. All I did was take the square root of 5 and make it an x. Now I think at this point in the course, this should be very easy for you to do. You know that the x has an imaginary 1 and that all you're going to do is just add the coefficients. So 3 minus 4 is negative 1. Negative 1 plus 1 turns out to be 0. Well, in this problem, the exact same thing happens. We have a coefficient of 1 that we almost never write in algebra. When you look at these, they all share the same radical that's underneath. They cannot be reduced. Therefore, you add the coefficients, and this answer is 0. 0 radical 5 and 0 are the same thing, but I don't think the teacher wants to see 0 radical 5.
That's right. In the same way that we don't want to see 0x or 0y, we just want the answer 0.
Now, our next problem, you'll notice we do not have like radicals, so we cannot apply the rule of taking 1 minus 4 and making this 3 something. In order to add and subtract radicals, we have to follow the same principles that we were using earlier in the course. That is, these values must be the same.
In other words, we've got to make sure that we're only combining like terms. In this particular problem right now, these aren't like terms, but as Jerry will show you, once we've simplified the radicals, they will be like terms and they will be able to be combined.
So we start with the first one, and again, you have your perfect square list in front of you. The square root of 18 can be broken up into square root of 9 times square root of 2. Minus the 4, I'm just going to write it down, and then 50 can be broken down into the square root of 25 times the square root of 2. So we have our perfect squares, 25 and 9. Now, further simplifying this, that's a 3, and this right here is a 5. So now here's our new problem. 3 radical 2 minus 4 times 5 is 20. Carry down the radical 2. So now, just like we were doing over here, 3 take away 20 is negative 17. And you just carry down the square root of 2.
Right, in exactly the same way that 3x minus 20x is negative 17x, 3 the square root of 2 minus 20 the square root of 2 is negative 17 the square root of 2. It's basically the same idea. If you understand how to combine like terms with variables, then you just do the same thing with radicals.
Now our last problem in this little section is about as hard as they can get. Again, we see none of the radicals are common, so we can't just go and start adding or subtracting here. So we're going to start, write down our 5, and then break down 8, which is 4 times 2. Plus 75 is divisible by the perfect square, 25, and 25 times 3 is 75. Minus 72 will give you a little headache in the beginning, but once you look at the biggest one, you'll see that 36 times 2 is 72. So we now have all of ours broken down, and albeit we couldn't get as close as we wanted, but wrapping this problem up, we know that that's a 2, this is a 5, and this is a 6. So now rewriting it gives us 5 times 2, which is 10 radical 2, plus 5 square root of 3, and be very careful with your signs, make sure you're carrying those down, and then minus 6 square root of 2. Now, you might notice that we have radical 2's and radical 3's. Well, this is kind of like, I'll do one of our little think bubbles over here. This is kind of like 10x plus 5y minus 6x. Now, I think you know that that y term you can't do anything with, but the two x's you can combine and make 4x and then carry down your 5y. Same principle here. We will combine these two. That'll give us 4 square root of 2, and then carry down the 5 radical 3. And that is your final answer.
All right, so finally all that leaves now is multiplication of radicals, so let's look at that.
Okay. Since we were just kind of breaking problems down into multiplication of radicals, these problems we're going to go in reverse. We're going to go from 2 radicals to 1. Then we'll address whether we can do anything with them. So 2 and radical 10. When you multiply them, you just take 2 times 10, and that gives you 20. You say, okay, am I finished, Professor? Not quite.
No, because again, once you've done the multiplication, you have to make sure that the radical can't be simplified. In the same way that we generally don't consider a fraction problem completed until you've reduced it to lowest terms, we don't consider a radical problem to be completed unless the final radical is reduced to lowest terms as well.
So with the square root of 20, we know 20 is divisible by 4, and 4 times 5 gives us 20. And then we take the square root of 4, which is 2. Carry down the square root of 5, and this is our final answer, 2 radical 5.
And notice in particular in this problem, the final answer doesn't look much of anything like the original problem, and that'll be the case in a lot of these radical problems. You really have to go through the multiplication and then the simplifying. There's no real shortcut way to get to the answer.
Okay, our second problem, we have radicals and numbers. Just to emphasize the rule here, the 2 and the 3, and I don't want to imply that this is a binomial here. This is a monomial times a monomial. I'm just drawing a line to emphasize that this 2 can only multiply this 3, and this radical can multiply that radical. So we end up with 2 times 3, which is 6, and then radical 6 times radical 6 is 36. Now, just like we did on our last problem, we look at this and we go, can we do something with 36? And the answer is yes. The square root of 36 is one of our perfect squares. So out comes a 6. Now, this is implied multiplication, so we end up with the answer of 36.
That's right. Sorry, Jerry. But anyway, remember that anytime two things are next to each other in algebra, we always understand that to be multiplication. So once we've simplified all of these different pieces, they're still being multiplied together. So the final answer is just 6 times 6, or 36.
Okay, our next problem, now we're going to involve the distributive property, and then over here, the FOIL method. Starting with the first one, we're going to take this times this term, and then this times this term. Now, when we multiply radical 2 times 2 radical 3, remember, there is an imaginary 1 here. Okay, so the 1 times the 2, these two on the outsides multiply together, give us 2, and then the radicals, what's underneath, multiply together to give us radical 6. So that first term times this is 2 radical 6. Then we do the same thing over here. 1 times the imaginary 1 is still 1, and we're going to leave that off, and then 2 times 7 is 14. You then ask yourself, okay, do any of my perfect squares divide 6 or 14? And in this case, the answer is no. So this is it. Don't add any more work than you need to.
Right, and again, recall, you can't simplify that because the square root of 6 and the square root of 14 aren't like terms, so that's the final answer. There's nothing else you can do.
Now, moving over here, this is a binomial and a binomial, so that means we're thinking of the FOIL method. So we're thinking of this times this, then this times this. We'll start with that, and then we'll end up with the 5 times each term. So, starting out, again, if you still need to write the ones in, that's up to you, but radical 3 times 2 radical 3 is 2 radical 9. Now, radical 3 times the negative 5 is negative 5 radical 3. Now you move to the 5. 5 times 2 radical 3, you can multiply the 5 and 2 together. That'll give you 10 along with the radical 3. And then 5 times negative 5 is negative 25. Now, we at least see two like terms here and here. But you might also notice that the square root of 9 is not in lowest terms out in front. So we have a couple things we need to do. Step 1, take care of the radical 9 and make it a 3. And we'll go ahead and combine these two. So our new problem gives us 6 plus 5 square root of 3 minus 25. Now again, we still have some like terms, the numbers. And some of you may have decided to go ahead and write a 6 out here in the beginning. I like to do it in 2 steps, not to overwhelm the student. So 6 take away 25 is negative 19. Carry down the 5 radical 3. These are not like terms. And Bill, I know you have a comment because we see a lot of this.
Right. What I was going to say is a very common wrong mistake now is to give the answer negative 14, the square root of 3. And again, you can't combine those because they're not like terms. Also, you may notice that we put the number part first and the radical second. And usually in problems like this, that is the order. It's not actually wrong if you write 5 the square root of 3 minus 19, but usually we want the number first and the radical second. The only other thing I'd add is if you find the FOIL method more difficult, you can still do these problems the way we did the problems in a previous chapter and write out the individual steps. So just to be clear what I'm talking about, that original problem is the square root of 3 times 2 the square root of 3 minus 5 plus 5 times 2 the square root of 3 minus 5. That is the first thing times this second thing, and the second thing times this second thing. And if you now multiply this out, you'll get exactly what Jerry has here. But sometimes students find these problems particularly frustrating, so I wanted to make sure I at least wrote this down.
Okay. And again, just to emphasize, that is your final answer for that problem. Well, Bill,
All right.
this wraps up chapter 12.
All right, that's the end of chapter 12. You realize you have only 2 chapters left and you've completed the entire course. This time I think we're going to go get some linguine or something. So we'll see you guys in chapter 13.